Hey friends, welcome back to your channel on J Physics Maniac. So we are starting a very new exciting series today. Today we are going to start a series which is essentially JE Advanced Plus. A course will be really helpful for different international Olympiads. It will cover the topics which are not generally available in commonly available books, and we will go through detailed discussion of concept and derivations, right? So without wasting much time, let us start. So the topic in this particular series of lecture we are going to cover is back body radiation. All right? Yeah. So before studying black body radiation, let us go through few fundamental basics. The first line that we need to understand and we need to keep in our mind is that hot bodies in condensed state is always they are always emitting radiations. They are always emitting radiations of continuous wavelength range, within bracket, rather than discrete. Okay, so let us understand the point. What do you mean by this? Whenever we are talking about hot bodies in condensed state, so this particular term condensed state, here we are basically referring to solids or liquids. So what happens? So since the solids and liquids at all the bodies which are available in nature have temperature, because of the temperature they are always emitting radiations, and those radiations are not discrete. They are having a wavelength range which is continuous. So what happens practically? The thing, if I talk about the chain of events that take place over here, is think about this matter that when we talk about temperature, how it is affecting this entire phenomena that we are going to study right now is, see, if I talk about giving heat or radiation falling on a body. If the radiation falls on a body and this radiation is absorbed, suppose this radiation is absorbed. If this radiation is absorbed, then this absorbed radiation will increase the kinetic energy of constituent. This will increase the kinetic energy of constituent atoms, and this increase in kinetic energy, basically it is the measure. We can write here that the average translational kinetic energy, is the measure of temperature. There again, one word is very important, that is translational. So please keep it in your mind. Rotational or vibrational will not contribute to temperature. So which particular term will contribute to temperature? It is only the translational kinetic energy of the atoms. So what is happening here? Radiation is falling on the body, it is getting absorbed, and because of this, the atom's average translational kinetic energy is increasing, and because of that, temperature of the body is rising. It is rising. On the other hand, another phenomenon is taking place simultaneously. What is that tree? If we have to understand that tree, that whenever the atoms are having increased kinetic energy, the electrons inside also oscillate. So if the electrons inside oscillate according to classical electromagnetic theory, classical EM theory, what will happen? That an accelerated charged particle an accelerated charged particle will emit radiation. So this electron is oscillating, and according to classical electromagnetic theory, an accelerating charged particle will emit radiation. Hence, this electron will emit radiation. Rather, it is better to say that the electron will help in emitting the radiation. Now, when it is radiating energy, so this will cool down. So it cools down. Since it cools down, temperature decreases. So on one hand, absorption of the radiation was increasing the temperature. On the other hand, emission of electromagnetic radiation by means of classical electromagnetic theory was decreasing the temperature. One occasion will come when as a note we can write that rate of absorption will be equal to rate of emission, and this particular status of rate of absorption is equal to rate of emission. This is basically termed as thermal equilibrium. So I hope this basic idea of how things are getting started off is clear. Once it is done, let us go on to the second segment. Here we will try to find out what do we actually mean by blackbody radiation. Very simple to understand. You take any object. So I am taking any random body. Any random body, let us assume that here we have incident radiation. So this one is basically incident radiation. Now, one part of this incident radiation, if I say that, let us say this body seems to be yellow in naked eye. So that means to our eyes, we are seeing the color of the body is yellow. That means that out of incident radiation, all other frequencies are absorbed except the color yellow. So this one is reflected. So that means whenever we see the colored object, how it is seen as colored object, it means whatever light is incident on that particular object, all other colors then except the color of the body is absorbed through the pigments of the body. So there is a reflected ray or reflected radiation. Other than that, in the first line I told that all hot bodies we will have thermal radiation. Now there is a problem. So we have two types of radiation over here. One is this type and another one is this type. So there are two types of radiation we have. We don't have any filter to differentiate this radiation, this one, from this one. No filter can distinguish from one another. So now what I will do, I will prefer to make a body or construct a body. Now I am modifying the situation. So we are taking a modified body so that the body is made in such a way, that when incident light is falling on it, if there is an incident radiation, so this one is the incident radiation, entire radiation will be absorbed. So this one is basically absorbed. So if this entire radiation is absorbed, we are left with only one kind of radiation that is coming out of the body, that is the thermal radiation. So since the incident ray which is falling on the surface is totally absorbed, nothing is coming out of this. So this body here, how this will appear? It will appear to be black. Please understand, since entire incident ray falling on the body is absorbed, nothing is reflected, so the body will appear to be black. And then this thermal radiation which is coming out of the body is basically called black body radiation. I hope you have a perfect concept now ki what we exactly mean by black body radiation. Right? Now, what is an ideal black body? I'm not going to the materialistic construction. I'm directly taking an example of the finest example that is given in case of black body. It is called cavity radiation. Please try to understand what do we mean by this cavity radiation. In case of cavity radiation, we take a closed enclosure. In this closed enclosure, a small opening is left. Inside the enclosure, a pointed notch is being created. Inner surface is blackened out. So inner surface is blackened. Now, on this particular pointed surface, an incident radiation is made to fall upon. So, the notch is prepared in such a way that after falling on this surface, it will go through multiple diffused reflection inside the cavity. So, by means of this multiple reflection inside the cavity, ultimately the ray will be trapped inside the cavity. Virtually nothing will come out. Only a very tiny small portion will be able to come out. 99.99% is absorbed. Since this ray is absorbed, so it is acting as perfect absorber. Now please pay attention. So here it is acting like a perfect absorber. So when this ray is trapped inside, now what I do, I take the same enclosure. I'm taking the same enclosure, and now here we have this small opening, and this is kept in a hot bath. When it is kept in a hot bath, what will happen? From the inner walls, thermal radiation will start getting generated. Here, thermal radiation will be generated. Now, if you increase the temperature of the hot bath, more and more thermal radiation will be generated, and when the entire space inside will be filled with this thermal radiation, suddenly we will observe that radiation is coming out through the cavity. Here in this case, it is behaving like a emitter. It is the same object that I have taken on two different circumstances. Once it was acting like an absorber, now it is behaving like a emitter. So basically this construction is called Ferri's black body. It is called Ferri's black body. So I hope the idea is clear, and that's why we can put a note here. What note? We comment here that a perfect black body is a good absorber as well as a good emitter. Right? I hope this idea is also clear. We got a perfect clarity on what is a black body radiation, how the black body is constructed, what do you mean by cavity radiation, how it is acting like a perfect absorber, and then how it is acting like a perfect emitter. Now, if I have to quantify the absorption or radiation, so here comes one law that is called Stephen's law. Basically, Stephen gave his experimental observation in the year of 1879, then later Boltzmann. He gave the mathematics in 1885 or 84, something like that, and then combined it is called Stephen-Boltzmann law. What is that? As per the law, we can write that the radiation or rate of emission or the rate of absorption both dq dt, rate of emission, it is proportional to the fourth power of temperature. In equation format we write minus EA sigma T to the power 4. And here in this case, dq dt is equal to, write small a capital A sigma T to the power 4. Here this minus sign is indicating, that energy is losing out by means of emission. And here positive sign is indicating, this positive sign is indicating that energy is getting absorbed. Other than that, this small quantity E is basically called emissivity, and this small a is called absorptivity. What do you need to know? That for a perfect black body, E is equal to A is equal to 1. So here this dq dt will basically turn out to be A sigma T to the power 4. So that is the rate of energy reflection, emission or absorption. So this rate of energy per unit area, it will give us power per unit time. So there this P becomes sigma T to the power 4. So this is basically Stefan-Boltzmann law. I repeat once again. Stefan carried out the experimental observation at 1879, and then Boltzmann pitched in with the mathematics. So thereby this mathematical form is combined, called Stefan-Boltzmann law. But what is the experimental observation in Stefan-Boltzmann law? That is more significant here. So for that we need to plot a graph. In this graph, please observe, along a y-axis we plot spectral energy density. Along x-axis frequency is plotted, and the graph, it comes like this. So there are very nice observation. What is the first observation? First observation says that for a particular frequency, every single frequency is associated to a specific spectral energy density which only depends on temperature, completely independent of the chemical composition of the body or the shape of the body. First point is very important. So observation number 1 is every frequency is associated to a value of spectral energy density which only depends on temperature, within bracket, independent of chemical composition of the body or shape of the body. Very important observation. Be careful about that and try to remember this particular observation. We will be using this whenever we are going to derive the Rayleigh-Jeans law. Correct? Fine. This is one observation. Second observation is what? Second observation is also very important. It says that whenever nu is increased, then the graph attains a peak and then again falls to 0 for higher value of nu. You can see that the graph is slowly increasing whenever you are moving from this point in the rightward direction. With the increase in nu, the graph is increasing. It is attaining a maximum value over here for a specific value of nu maximum. Here you have the highest value of spectral energy density, and then further increase of nu, the graph is approaching to 0 once again. That is the second observation. What about the third observation? Third observation says, and this particular graph is basically at a particular temperature, let us say T1. Third observation says if temperature is increased, further increased, then we'll observe that different graphs are coming, but they are coming like this. So let us say this graph is for temperature T2, and another, again, if we further increase the temperature, this graph we get is for temperature T3. So because of this increase in temperature, the peak you can see is shifting on the rightward direction. So if T increases, then the peak shifts towards higher frequency. Within bracket, immediately when you write higher frequency, you have to remember lower wavelength. That means if instead of putting frequency on the x-axis, if we put wavelength, then this peak here, they will be shifting in the leftward direction. So the peak shifts toward higher frequency side. So from here, I can do another conclusion. That conclusion is nu maximum is proportional to temperature. So if nu maximum is proportional to temperature, nu maximum means we know C by lambda maximum, that is proportional to temperature. So their product, which one is that? Lambda maximum into T, it comes to be some constant which is referred as B. Now here I got another law, that is nothing but Wien's displacement law. This is Wien's displacement law, right? So that's the basic sampling about what is blackbody radiation, what do we mean by normal radiation, how radiation comes out, what is the example of blackbody radiation, and what are the observations around the blackbody radiation. So this lecture is up to this only. In the next lecture, we are going to come up with Rayleigh-Jeans derivation, how the ultraviolet catastrophe plays a role in this particular discussion. Thank you for watching the video. If you do like this video, do like, share and subscribe.